Late March 1945, a railway siding near Schwetzingen, Germany. American intelligence officers from the 12th Armored Division stared at what would become one of the war's most revealing technical discoveries. A Jagdpanther tank destroyer sat motionless on a flatbed railcar, abandoned mid-transport, its long 71.5mm gun angled skyward like a silent accusation. The crew had vanished. No demolition charges had been set. Through the chaos of Germany's collapsing Western Front, someone had left their most lethal tank destroyer for the enemy to claim intact. What American engineers would learn from this 46-ton steel predator would prove more devastating to German prestige than destroying a dozen Jagdpanthers in combat. The vehicle would reveal not just sophisticated engineering and tactical brilliance, but a catastrophic mechanical fragility that rendered even the most fearsome weapon a liability on extended campaigns. Not through inadequate armor or insufficient firepower, but through an engine so unreliable it could barely complete 80 miles before suffering catastrophic mechanical failure. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. The Jagdpanther represented the pinnacle of German tank destroyer design. Introduced in January 1944, it mounted the formidable 88mm Park 43L-71 gun, the same weapon that equipped the fearsome King Tiger heavy tank. This gun could penetrate any Allied tank's frontal armor at ranges exceeding 2,000 meters. The Jagdpanther's sloped armor, measuring 80mm thick on the front superstructure at 55 degrees, made it virtually impenetrable to most Allied anti-tank weapons when engaged frontally. Its low silhouette, barely 2 meters tall, made it difficult to spot and nearly impossible to hit at long range. German propaganda films showcased the Jagdpanther as the ultimate tank killer, claiming it combined the firepower of the heaviest tanks with the speed and agility of medium tanks. Allied intelligence reports from late 1944 described encounters with a new German tank destroyer of exceptional lethality. British forces in Normandy first reported these vehicles in August 1944 near Falaise. American units encountered them during the German counteroffensive in the Ardennes in December 1944. Every report emphasized the same characteristics: devastating long-range firepower, excellent armor protection, remarkable battlefield effectiveness, and mysterious tendency to be found abandoned with no apparent battle damage. The Jagdpanther program had begun in late 1942 as a response to Soviet tank development. German forces on the Eastern Front faced increasing numbers of 34 medium tanks and new, heavy tanks like the KV-1 and IS-2. Existing German tank destroyers like the Marder and Nashorn mounted powerful guns but had minimal armor protection, making them vulnerable to Soviet return fire. German High Command demanded a new tank destroyer combining heavy firepower with strong armor protection and good mobility. The contract went to MIAG, Maschinenbau und Bombbedarf AG, a company experienced in armored vehicle production. Design work proceeded through 1943, with the first prototype completed in October 1943. The Jagdpanther utilized the chassis of the Panther medium tank, itself introduced in mid-1943 following German experiences against Soviet 34s. The Panther chassis provided excellent mobility and a proven suspension system. Engineers mounted a fixed superstructure housing the massive 88mm gun, eliminating the weight and mechanical complexity of a rotating turret. This configuration allowed thicker armor protection while keeping overall weight manageable at 46 tons. Production began in January 1944 at 3 manufacturing facilities: MEAG in Brunswick, MNH in Hanover, and MBA in Berlin. Initial production targets called for 150 vehicles monthly, but German industrial capacity under constant Allied bombing could never approach these numbers. Actual monthly production peaked at 42 vehicles in July 1944 and averaged only 27 vehicles monthly throughout 1944. By war's end in May 1945, total Jagdpanther production reached approximately 415 vehicles, far below the 2,000 originally planned. From the beginning, the Jagdpanther program suffered from the same affliction, crippling all late-war German armoured vehicle production. The requirement to use the Maybach HL230 P30 engine. This power plant, originally designed for the 30-ton Panther tank, was being pressed into service in vehicles significantly heavier. The Jagdpanther weighed 46 tons in combat configuration. The engine produced 690 horsepower at 3,000 revolutions per minute, giving a power-to-weight ratio of 15 horsepower per ton. This was adequate for road movement but marginal for cross-country operations, especially when the vehicle carried full ammunition, fuel, and crew. More critically, the HL230 engine was never designed for the sustained high-power operation required in heavy combat vehicles. German engineers had developed it in the late 1930s for medium tanks operating at lower combat weights. Forcing it to propel 46-ton vehicles subjected engine components to stresses beyond design specifications. Pistons, connecting rods, crankshafts and cooling systems operated continuously at maximum capacity with no safety margin. The predictable result was catastrophic mechanical failure after relatively brief operational periods. German military testing of early production Jagdpanthers in late 1943 and early 1944 revealed troubling reliability problems. Test vehicles suffered engine failures during acceptance trials before even reaching combat units. Maybach engineering reports documented connecting rod failures, crankshaft bearing failures, and cooling system inadequacies. When engineers reported these problems to Wehrmacht procurement offices, they received orders to continue production. Germany needed tank destroyers immediately. Reliability improvements would have to wait until the military situation stabilized. That stabilization never came. First combat deployment of Jagdpanthers occurred in June 1944 in Normandy. Heavy Panzerjäger Battalion 559 received approximately 24 Jagdpanthers and deployed to counter the Allied invasion. Initial combat reports praised the vehicle's firepower and armor protection. Crews reported destroying Churchill and Sherman tanks at ranges exceeding 1,800 meters with single shots. The sloped armor defeated Allied tank guns and anti-tank weapons repeatedly, but maintenance sections reported alarming engine failure rates. Within the first 2 weeks of combat operations, 11 of 24 Jagdpanthers suffered major engine failures, requiring complete engine replacement. Replacement engines were unavailable. The battalion's war diary from July 1944 documented the deteriorating situation. July 7th entry reported excellent tactical success, with 16 Allied tanks destroyed in defensive operations near Tilly-sur-Seulles. However, 4 Jagdpanthers were immobilized from engine failure during the engagement. One vehicle's engine had seized completely after approximately 60 kilometers of total operation since delivery from the factory. July 14th entry noted 8 Jagdpanthers operational from original strength of 24. 5 were down from engine failures, 7 from battle damage, and 4 had been destroyed by their own crews during withdrawals when recovery proved impossible. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel, it means a lot to us. Now, back to the story. July 23rd entry captured the crisis starkly. Impossible to maintain operational readiness. Engine failures occur faster than combat losses. Request priority allocation of replacement engines. Headquarters response came 3 days later. No engines available. Make do with existing resources. August brought intensified combat as Allied forces attempted to encircle German positions in the Falaise pocket. Battalion 559 participated in desperate defensive operations, trying to hold escape routes open. The battalion war diary's final entries before capture in late August told a story of technological collapse, matching tactical disaster. August 10th. 3 Jagdpanthers operational, all others immobilized from mechanical failure or battle damage. Cannot conduct mobile defense without operational vehicles. August 15th. Orders to withdraw. Only 1 Jagdpanther capable of movement under own power. Attempting to tow others but lacking adequate recovery equipment may be forced to demolish vehicles. August 19th. All remaining Jagdpanthers abandoned during withdrawal. Demolition teams overwhelmed. Several vehicles left intact for enemy capture. Battalion effectively destroyed as combat unit. British forces recovered 2 intact Jagdpanthers from the Falaise pocket in late August 1944. Both vehicles had been abandoned with empty fuel tanks, but no apparent battle damage. British technical intelligence teams conducted preliminary examinations and forwarded detailed reports to American intelligence. The reports emphasized the Jagdpanthers' formidable combat capabilities, but noted that both captured vehicles showed evidence of severe engine problems. One vehicle's engine had catastrophically failed with a broken crankshaft. The other's engine appeared functional, but maintenance logs found inside the vehicle indicated it had suffered repeated overheating problems and was due for complete engine replacement after only 83 kilometers of operation. These British reports reached American intelligence sections in September 1944, but actual American examination of a Jagdpanther would wait until 1945. The Ardennes offensive in December 1944 brought American forces into direct contact with Jagdpanthers for the first time. Heavy Panzerjäger Battalion 560, deployed to support the 6th SS Panzer Army's northern thrust toward Antwerp. The battalion fielded approximately 28 Jagdpanthers at the offensive's start on December 16th. American after-action reports from units engaged in the Ardennes documented Jagdpanther effectiveness and limitations simultaneously. The 1st Infantry Division encountered Jagdpanthers near Butgenbach on December 18th. Combat reports described devastating long-range fire destroying M4 Sherman tanks and M10 tank destroyers at distances where American return fire proved ineffective. However, within 48 hours, reconnaissance patrols found 3 Jagdpanthers abandoned along approach routes with no battle damage visible. Engineers examining the vehicles found all 3 had suffered catastrophic engine failures. One vehicle's engine had literally broken apart internally, with connecting rods punched through the engine block. The 2nd Armored Division met Jagdpanthers during counterattacks near Selles in late December. Battalion 560 had advanced approximately 90 kilometers from its starting positions when fuel shortages and mechanical breakdowns began immobilizing vehicles across the entire German offensive. American forces found Jagdpanthers abandoned throughout the operational area. Technical intelligence teams documented each find carefully. A pattern emerged immediately. Most abandoned Jagdpanthers showed no combat damage but had suffered complete mechanical failure, primarily engine-related. Captain James Richardson, technical intelligence officer with 12 Corps, filed a detailed report on January 8, 1945, summarizing findings from examination of 17 abandoned German armored vehicles, including 6 Jagdpanthers. His report noted that of 6 Jagdpanthers examined, 5 had suffered catastrophic engine failure. The 6th had thrown a track and been abandoned when recovery proved impossible, but even this vehicle showed evidence of severe engine problems, including cracked engine block and failed cooling system. Richardson's report concluded that the Jagdpanther, while tactically superior to American tank destroyers, suffered from profound mechanical unreliability that severely limited its operational effectiveness. He recommended that priority intelligence effort be directed toward obtaining an intact Jagdpanther for comprehensive technical evaluation at Aberdeen Proving Ground in Maryland, the United States Army's premier testing facility for captured enemy equipment. That opportunity came in late March 1945 as American forces drove deep into Western Germany. The 12th Armored Division, advancing rapidly toward the Rhine, discovered a railway marshalling yard near Schwetzingen containing numerous German military vehicles in various states of abandonment. Among them sat a Jagdpanther on a railway flatcar, apparently being evacuated eastward when the transport collapsed. Lieutenant Colonel Robert Hayes, commanding Combat Command B of 12th Armored Division, recognized the intelligence value immediately. He assigned a security detail and notified Corps headquarters of the find. Within 24 hours, technical intelligence officers arrived to assess the vehicle's condition and arrange recovery. The Jagdpanther bore tactical number 3, 1, 2, and had belonged to Heavy Panzerjäger Battalion 512, a unit that had been defending the Rhine approaches before being overrun by American advances. The vehicle sat complete and intact. The 88mm gun remained functional. Ammunition racks held 32 rounds of armor-piercing ammunition. Personal equipment, tools, and maintenance records lay scattered inside the fighting compartment, apparently abandoned in haste. Most significantly, the engine compartment showed clear evidence of catastrophic mechanical failure. The engine would not start. Preliminary examination revealed extensive internal damage. Intelligence officers photographed everything, collected all documentation found with the vehicle, and arranged for the Jagdpanther to be transported to the nearest port facility for shipment to the United States. The recovery operation demonstrated German over-engineering even in failure. The Jagdpanther's weight and dimensions challenged American recovery equipment designed for 30-ton Sherman tanks. Multiple M32 tank recovery vehicles were required working together to load the Jagdpanther onto a heavy transport trailer. The convoy moved primarily at night to avoid any remaining Luftwaffe activity, though by late March 1945 German air power had virtually ceased to exist over Western Germany. Engineers had to verify bridge load ratings along the route. Some bridges could not support the combined weight of the Jagdpanther and its transport trailer, forcing lengthy detours. The journey from Schwetzingen to the port of Antwerp took 9 days for a trip that normally required 12 hours. At Antwerp, loading the Jagdpanther aboard ship for Atlantic crossing presented another engineering challenge. The vehicle and its shipping cradle weighed over 50 tons combined. Port, engineers used heavy-lift cranes rated for 70 tons to load the vehicle aboard a Liberty ship designated for military cargo transport to the United States. The Atlantic crossing took approximately 3 weeks, with the ship arriving at Norfolk, Virginia in late April 1945, just days before Germany's final surrender. From Norfolk, the Jagdpanther travelled by special reinforced flatbed railway car to Aberdeen Proving Ground, arriving in early May 1945. Aberdeen Proving Ground had been evaluating captured German armoured vehicles throughout the war. Engineers and technical intelligence officers had developed comprehensive testing protocols covering armour protection, armament effectiveness, mechanical reliability, mobility characteristics, and logistical sustainability. The Jagdpanther, designated as Vehicle 312, would receive the most thorough examination possible. Brigadier General Gladion M. Barnes, Chief of Research and Development for Army Ordnance, issued explicit instructions. The captured Jagdpanther represented an unprecedented opportunity to evaluate Germany's most advanced tank destroyer design. Testing would be comprehensive, but mechanical reliability would receive absolute priority. British intelligence reports and field observations from the Ardennes had indicated severe reliability problems. Aberdeen testing would determine definitively whether these problems were inherent to the design or resulted from poor maintenance and combat damage. Initial inspection of Jagdpanther 312 took place in late May 1945. Engineers documented every aspect of the vehicle's construction, taking detailed measurements and photographs. The Jagdpanther's engineering impressed American engineers immediately. The vehicle combined several advanced design features rarely seen in American armored vehicles. The suspension system used overlapping road wheels with torsion bar suspension, providing excellent weight, distribution, and cross-country mobility. The sloped armor design deflected incoming projectiles effectively, maximizing armor protection without excessive weight. The massive 88mm Pak 43 gun represented the ultimate development of Germany's famous 88mm series, capable of penetrating any Allied tank at extreme ranges. But the engine told a different story entirely. Engineers removed the Maybach HL 230P30 engine for detailed examination. What they found shocked even veterans who had examined hundreds of German vehicles. The engine had suffered catastrophic internal failure. The number 7 cylinder connecting rod had broken completely, destroying the piston, punching through the engine block, and damaging the crankshaft beyond repair. Secondary damage included broken number 5 and number 8 connecting rods, damaged crankshaft bearings, and fractured oil pump housing. Coolant had leaked internally, mixing with engine oil, and creating sludge throughout the lubrication system. The engine was completely unsalvageable, damaged beyond any possibility of repair or rebuilding. More significantly, examination revealed that this catastrophic failure had occurred after minimal operational use. Maintenance records found with the vehicle indicated Jagdpanther 312 had been delivered to Battalion 512 in February 1945. The vehicle had participated in defensive operations for approximately 6 weeks before being abandoned. Total operational distance recorded in the maintenance log showed 128 kilometers, approximately 80 miles. The engine had failed catastrophically after less than 80 miles of combat operation. Aberdeen engineers initially suspected battle damage or poor maintenance might explain the catastrophic failure, but detailed metallurgical analysis eliminated both possibilities. The connecting rod that had broken showed no impact damage, no stress fractures from external force, and no evidence of improper installation or assembly defects. Instead, microscopic examination revealed classic fatigue failure patterns. The rod had broken from repeated stress cycling beyond its design limits. The metal had failed from being asked to do more than it was engineered to withstand over extended periods. Engineers examined the remaining intact connecting rods and found alarming evidence throughout. Every rod showed advanced fatigue cracking in various stages of development. Some cracks had propagated halfway through the rod cross-section. Others showed surface cracking that would inevitably deepen with continued operation. None of the connecting rods would have survived another 50 kilometers of operation. All were approaching catastrophic failure. The crankshaft told the same story of components operating beyond design specifications. Bearing journals showed severe scoring and material loss. Main bearings had worn so extensively that crankshaft movement exceeded acceptable tolerances by factors of 3 to 5. The crankshaft itself showed torsional stress cracks in 2 locations. Engineers concluded that complete crankshaft failure would have occurred within another 20 to 30 operational hours, even if the connecting rods had somehow survived. The engineering team prepared a preliminary report in June 1945, analyzing the failure mechanisms. The report identified fundamental design inadequacies in applying the Maybach HL230 engine to vehicles weighing 46 tons. The engine had been designed originally for tanks weighing approximately 30 tons. Increasing vehicle weight by over 50% without corresponding engine strengthening subjected all internal components to stresses exceeding design parameters. Connecting rods designed for 30-ton vehicle loads experienced 50% higher stress loads in the Jagdpanther. Over thousands of stress cycles during normal operation, these higher loads caused accelerated fatigue crack development. Components designed for perhaps 500 operational hours in 30-ton vehicles might last only 150 to 200 hours in 46-ton vehicles before fatigue failure. But the preliminary report identified an even more critical problem. German engineers had increased engine output from 650 horsepower in original HL230 versions to 690 horsepower in the HL230P30 variant used in Panthers and Jagdpanthers. This power increase came from higher compression ratios and increased maximum engine speed. Higher compression and higher speeds subjected internal components to even greater stresses. Components already stressed beyond design limits from increased vehicle weight now operated at higher power levels, multiplying stress factors geometrically rather than arithmetically. The result was predictable mechanical catastrophe. Aberdeen engineers calculated that the HL230P30 engine in the Jagdpanther operated under combined stress loads approximately 2.3 times higher than the engine's original design specifications. No engine could sustain such operational abuse for extended periods. Catastrophic failure was not a possibility but an absolute certainty. The only variable was when failure would occur, not whether it would happen. With Jagdpanther 312's engine destroyed beyond salvage, Aberdeen engineers faced a critical problem. Comprehensive testing required a functional vehicle. They needed another engine. The solution came from captured German stocks. American forces had overrun numerous German supply depots during the final offensive into Germany. Among captured equipment were approximately 30 Maybach HL230 engines of various subtypes, some new in crates, others removed from damaged vehicles for rebuilding. Aberdeen requested and received 3 engines in July 1945. Engineers installed the best condition engine in Jagdpanther 312 and kept the other 2 as spares, anticipating they would need them. The testing program began in August 1945 and would continue for 8 months through March 1946. The scope was comprehensive, covering every aspect of Jagdpanther performance, but mechanical reliability dominated the test schedule because field reports had indicated this was the vehicle's critical vulnerability. Initial road testing began in mid-August on Aberdeen's paved test circuit. Engineers wanted baseline data under ideal conditions before attempting more stressful evaluations. The Jagdpanther performed well initially. The vehicle reached 55 km/h on level pavement, matching German specifications. Acceleration proved adequate, though not exceptional. Braking performance exceeded expectations, with the vehicle stopping from 50 km/h in approximately 45 meters. Steering response was heavy but acceptable for a vehicle of this size and weight. After 80 kilometers of road testing, engineers conducted their first detailed mechanical inspection. What they found was disturbing. The engine showed signs of stress, far exceeding normal expectations for such limited operation. Connecting rod bearings showed measurable wear. Main bearing clearances had increased beyond new engine specifications. The number 3 cylinder showed slightly lower compression than the others, indicating early ring wear. Most concerning, slight oil weeping appeared around the number 6 cylinder base, suggesting possible head gasket problems developing. Engineers documented everything photographically and continued testing, but the early warning signs were clear. This engine was already showing stress damage after minimal operation under ideal conditions. Cross-country testing began in September 1945 using Aberdeen's rough terrain course. This track included hills, ditches, mud sections, water obstacles, and rough ground simulating combat conditions. The Jagdpanther's performance impressed test crews. The overlapping road wheel suspension provided excellent weight distribution and smooth ride quality, even over rough terrain. The vehicle negotiated obstacles that stopped lighter American tank destroyers. Ground pressure, despite the vehicle's 46-ton weight, remained acceptable due to wide tracks and efficient suspension design. But the mechanical toll proved severe. After only 40 kilometers of cross-country operation, engine temperature began climbing above acceptable limits. Engineers installed additional temperature monitoring equipment and discovered the cooling system operated at maximum capacity during cross-country movement. The radiator could barely dissipate heat generated by the engine, working hard to propel 46 tons across rough terrain. Any additional load would cause overheating. Test crews conducted exactly that experiment. They loaded the vehicle with additional weight, simulating full ammunition, maximum fuel, and combat equipment. Total weight increased to approximately 48 tons. Cross-country testing with this load caused immediate overheating. After only 15 kilometers, coolant temperature exceeded safe limits. Engineers stopped the test to prevent engine damage. Analysis revealed the fundamental problem. The cooling system, designed for the HL230 engine in 30-ton Panthers, was marginal for the same engine in 46-ton Jagdpanthers. During hard acceleration, climbing steep grades, or sustained high-power operation, the engine generated more heat than the cooling system could dissipate. Overheating led to accelerated component wear, oil breakdown, and increased risk of catastrophic failure. The cooling system inadequacy compounded all other reliability problems. Engineers conducted their second major mechanical inspection after 160 total kilometers of combined road and cross-country testing. The findings were alarming. Connecting rod bearing wear had progressed significantly. Clearances that had been slightly high were now excessively loose. Main bearing journals showed scoring that had not been present during the first inspection. The number 3 cylinder now showed compression loss, indicating ring failure was progressing. Most seriously, the head gasket on number 6 cylinder had failed, allowing combustion gases into the cooling system and coolant into the cylinder. This was early-stage failure, but it would rapidly worsen. Engineers replaced the failed head gasket and continued testing, knowing they were observing the systematic destruction of the engine in real time. October 1945 brought tactical testing, designed to simulate combat operations. Test scenarios included rapid acceleration from concealment, high-speed reverse movement, sustained firing with the main gun while maneuvering, and long-distance travel interspersed with combat simulation. These tests subjected the vehicle to conditions matching or exceeding actual battlefield requirements. The Jagdpanther excelled tactically. The 88mm gun demonstrated exceptional accuracy, placing shots within a 1-meter circle at 1,500 meters consistently. The powerful gun recoil system allowed rapid follow-up shots. Crews could fire, reverse into concealment, reposition, and fire again within 45 seconds. The low silhouette made the vehicle difficult to spot, and the heavy frontal armor defeated all American anti-tank weapons tested against armor samples. Everything about the Jagdpanther's combat performance validated German design objectives. But the mechanical performance collapsed. During one tactical scenario requiring rapid repositioning over a 2-kilometer course with multiple stops for simulated firing, the engine overheated so severely that test crews had to shut down and wait 30 minutes for cooling before continuing. During another scenario, simulating sustained combat movement, unusual knocking sounds developed in the engine. Engineers immediately stopped testing and conducted emergency inspection. The inspection revealed that connecting rod number 5 was developing a fatigue crack visible to the naked eye. The crack had propagated approximately 40% through the rod's cross-section. Continued operation would certainly cause complete rod failure, destroying the engine exactly as had happened to the original engine. Engineers photographed the cracked rod extensively, removed the engine, and installed the second spare engine to continue testing. At this point, Jagdpanther 312 had accumulated 312 kilometers of total operation. The first engine had arrived destroyed. The second engine had lasted 160 kilometers before developing multiple serious problems requiring replacement. Now, the third engine would be tested to destruction to gather complete data on failure progression. The third engine received intensive monitoring. Engineers installed sensors, measuring temperatures, pressures, and vibrations throughout the engine. Every component was photographed and measured before installation to establish baseline conditions. Testing would continue until catastrophic failure occurred, documenting the complete failure progression. Testing resumed in November 1945 with the instrumented third engine. Engineers initially conducted gentle break-in operation, running the engine at moderate speeds and loads for the first 50 kilometers. Even during this careful break-in, instruments showed concerning trends. Bearing temperatures ran slightly higher than specifications. Oil pressure showed minor fluctuations, suggesting bearing clearances were already loosening. Combustion pressures varied between cylinders more than ideal, indicating manufacturing tolerances were marginal. After break-in, engineers resumed full tactical testing. The instrumented engine provided unprecedented insight into how the HL-230P30 died. Under sustained high-power operation, cylinder head temperatures exceeded design limits by 20 to 30 degrees Celsius. Bearing temperatures climbed 15 to 20 degrees above specifications. Oil pressure dropped as bearing clearances increased from wear. Most revealing, vibration sensors showed that the crankshaft developed torsional oscillations during high-power operation. These oscillations subjected connecting rods to cyclical stress loads that progressively weakened the metal through fatigue. Engineers could literally watch the engine destroying itself in real time as instrument readings tracked the systematic degradation. By kilometer 400, multiple problems had developed. Number 2 cylinder showed compression loss from ring wear. Numbers 4 and 7 cylinders showed elevated temperatures indicating cooling problems. Main bearing clearances had increased to the point where oil pressure could not maintain proper lubrication. Connecting rod bearings showed measurable wear. The crankshaft vibration had increased noticeably. Test crews reported the engine ran roughly with vibration felt throughout the vehicle. At kilometer 432, During acceleration, up a steep grade under full load, catastrophic failure occurred. The engine suddenly seized with a tremendous metallic crash. Test crews immediately shut down all systems. When engineers removed the engine for examination, they found destruction even more complete than the original engine. Connecting rod number 4 had failed catastrophically, breaking completely. The broken rod destroyed the piston, punched through the engine block, and struck the transmission housing, cracking it. The flailing broken rod damaged 3 other connecting rods before the engine seized. The crankshaft showed multiple fractures from shock loads. The oil pump housing had shattered, spewing oil throughout the engine compartment. Secondary damage included damaged valve train components, broken rocker arms, and fractured cylinder head. The engine was destroyed so completely that salvaging any components proved impossible. Aberdeen engineers prepared their comprehensive mechanical reliability report in January 1946. The data painted a devastating picture of the Jagdpanther's fundamental weakness. 3 engines had been tested to destruction. The first arrived already failed after approximately 80 miles of combat operation. The second engine lasted 160 kilometers, roughly 100 miles, before developing problems requiring replacement. The third engine operated 432 kilometers, approximately 268 miles, before catastrophic failure. But this occurred under controlled test conditions, with careful monitoring and maintenance impossible in combat situations. The report concluded that the Maybach HL230P30 engine in the Jagdpanther application could be expected to operate approximately 100 to 150 kilometers, 60 to 90 miles, under combat conditions before catastrophic mechanical failure. This represented an operational life approximately 1/5 of comparable American engines in similar applications. The report identified the fundamental engineering failure. German designers had taken an engine designed for 30-ton vehicles and forced it to propel 46-ton vehicles at increased power output. This violated basic engineering principles regarding stress margins and component life. The predictable result was catastrophically short operational life, but the report went further, analyzing the strategic implications of such profound mechanical unreliability. A tank destroyer that breaks down after 80 miles cannot conduct mobile operations. It cannot pursue defeated enemies. It cannot redeploy rapidly to threatened sectors. It cannot retreat to defensive positions when required. A weapon that fails mechanically after minimal operation becomes a strategic liability regardless of its tactical superiority. The report compared Jagdpanther mechanical reliability to American tank destroyer designs. The M10 tank destroyer, mounting a 3-inch gun in an open-topped turret, weighed only 29.6 tons. Its General Motors diesel engine operated reliably for over 3,000 miles between major overhauls. The M36 tank destroyer, mounting a 90mm gun and weighing 38 tons, used a Ford GAA engine that typically operated over 2,000 miles before requiring major maintenance. Even accounting for the Jagdpanther's greater weight and more powerful armament, the reliability difference was staggering. American tank destroyers operated 10 to 20 times longer between major mechanical failures than Jagdpanthers. Colonel Robert Keller, Chief of the Foreign Material Branch at Aberdeen, compiled all testing data into a classified intelligence assessment distributed throughout Army Armor Commands in March 1946. The assessment emphasized that the Jagdpanther represented Germany's most advanced tank destroyer design, incorporating sophisticated engineering and excellent tactical capabilities. The 88mm gun could destroy any Allied tank at extreme range. The armor protection defeated all Allied anti-tank weapons frontally. The mobility and agility impressed test crews. But catastrophic mechanical unreliability negated these tactical advantages completely. Expected operational life of only 60 to 90 miles under combat conditions meant Jagdpanthers could not sustain extended operations. The assessment recommended that tactical doctrine emphasize forcing enemy armor to maneuver extensively. German heavy vehicles mounting the Maybach HL230 engine would break down from the mechanical stress of extended movement. Immobilized German armor could be bypassed or destroyed with artillery and air support, rather than risking direct engagement. The assessment distributed to field commanders in early 1946 came too late to affect World War II operations, but its lessons shaped post-war American tank design philosophy profoundly. Engineers understood that reliability was not merely a maintenance convenience, but a fundamental tactical requirement. A tank that breaks down becomes worse than useless. It becomes a liability requiring recovery assets, spare parts, and maintenance personnel that could be supporting operational vehicles. The United States military would never again field armored vehicles that sacrificed reliability for marginal improvements in firepower or protection. The strategic implications of Jagdpanther unreliability extended far beyond individual vehicle performance. Intelligence analysts cross-referenced Aberdeen test data with captured German unit records to understand how mechanical failures affected operational effectiveness across entire formations. The results revealed a pattern of systematic operational paralysis that crippled German armored forces during the war's final year. Heavy Panzerjäger Battalion 563 War Diary, captured intact by American forces in April 1945, provided devastating confirmation of Aberdeen's findings. The battalion had received 27 new Jagdpanthers in January 1945 and deployed to the Eastern Front in February. The diary documented mechanical catastrophe unfolding week by week. February 12, 1945. Battalion deployed with 27 Jagdpanthers to defensive positions near Kustrin. All vehicles operational upon arrival. February 19th. First engine failure occurred during repositioning movement. Vehicle 12 suffered complete engine seizure after 47 kilometers of operation. No, spare engine available. Vehicle abandoned in place. February 26th. 3 additional engine failures during week. Vehicles 8, 14, and 23 all immobilized. Maintenance section overwhelmed. Spare parts non-existent. March 5th. 7 Jagdpanthers now immobilized from engine failures. Battalion combat effectiveness reduced by 26% without firing a shot in anger. Remaining vehicles restricted to static defensive positions to minimize mechanical stress. March 14th. Soviet offensive broke through adjacent sectors. Battalion ordered to conduct mobile defense, but only 11 Jagdpanthers remained operational. 6 more had failed mechanically during previous week. Attempted mobile operations caused 3 additional engine failures within first day of movement. March 23rd. Battalion down to 6 operational vehicles from original 27. 21 Jagdpanthers lost to mechanical failure, not enemy action. Orders received to withdraw, westward, but insufficient operational vehicles to conduct organized retreat. April 2nd. Final diary entry before battalion dissolution. 2 Jagdpanthers remained operational. Both were immobilized by fuel shortage within 24 hours. Crews destroyed vehicles and retreated on foot. Battalion ceased to exist as coherent fighting unit. In 90 days of operations, the battalion had fired its weapons in anger perhaps a dozen times. Mechanical failures had destroyed the unit's combat effectiveness completely. Similar patterns appeared in every captured German unit diary from the war's final months. Heavy Panzerjäger Battalion 512, the unit that originally operated Jagdpanther 312, showed identical mechanical collapse. Battalion 512 had received 30 Jagdpanthers between December 1944 and February 1945. By March 1945, only 4 remained operational. The other 26 had been lost to mechanical failures, abandoned during retreats, or destroyed by crews unable to recover them. American intelligence analysts compiled comprehensive statistics from all available German records. Across all heavy Panzerjäger battalions equipped with Jagdpanthers, average operational readiness rates never exceeded 47%, even when units were not in combat. During active operations, operational readiness typically fell below 30% within 2 weeks, and below 20% within 4 weeks. These figures compared catastrophically with American tank destroyer battalions, where operational readiness rates typically exceeded 85%, even during intensive combat operations. The intelligence analysis revealed something even more significant about German armoured vehicle development during the war's final years. The Jagdpanther was not an isolated case of unreliability. Nearly every late-war German armoured vehicle suffered from similar mechanical problems. The Panther medium tank used the same Maybach HL-230 engine and experienced comparable reliability problems. The Tiger II heavy tank, weighing 69 tons, mounted a more powerful Maybach HL-230P45 engine that still proved inadequate for the vehicle's weight. The Ferdinand tank destroyer, the Elephant tank destroyer, the Jagdtiger super heavy tank destroyer all shared the same fundamental flaw: insufficient engine reliability for vehicle weight and combat requirements. German engineering had created tactically superior weapons that could not survive operationally long enough to matter strategically. The pattern suggested systematic failure in German armoured vehicle development philosophy during the war's latter half. Designers prioritized firepower and armor protection above all other considerations. Mobility received secondary consideration. Mechanical reliability appeared almost as an afterthought. The result was a fleet of armored vehicles that dominated individual engagements but collapsed mechanically during sustained operations. American analysts identified the critical decision point where German design philosophy diverged catastrophically from engineering reality. In 1942 and 1943, German designers faced a fundamental choice. They could design new armoured vehicles around available, reliable engines, accepting limitations in armour and firepower to maintain mechanical sustainability. Or they could push existing engines beyond design limits to achieve maximum combat capability, accepting reduced reliability as the price for tactical superiority. German High Command chose the latter option consistently. The Jagdpanther exemplified this choice perfectly. Designers knew the Maybach HL-230 engine was marginal for a 46-ton vehicle. They knew the cooling system was inadequate. They knew operational life would be severely limited. But they also knew the resulting vehicle would be tactically superior to anything the Allies fielded. They chose short-term tactical superiority over long-term operational sustainability. Post-war interrogations of German tank designers and engineers provided insight into the decision-making process. Heinrich Ernst Kniepkamp, who had served as chief engineer for the Waffenamt, the German Army Weapons Agency, testified to American interrogators in July 1945. His testimony, preserved in captured document records, explained the impossible situation German designers faced. Kniepkamp stated that by 1943, German industry could not produce more powerful engines in quantities sufficient to meet armoured vehicle requirements. The Maybach factories were already operating at maximum capacity, producing HL-230 engines. Developing and producing new engine designs would require at least 2 years and massive industrial investment. Germany did not have 2 years. Allied forces were advancing on all fronts. The German military demanded better tanks and tank destroyers immediately, not in 2 years. Designers received explicit orders to maximize combat capability using existing engine production. Reliability concerns were acknowledged but deemed secondary to immediate tactical requirements. Kniepkamp testified that engineers repeatedly warned military leadership about the reliability consequences of mounting heavy vehicles on inadequate engines. These warnings were received, understood, and overruled. The strategic situation demanded maximum firepower and armor protection, even if mechanical reliability suffered. German leadership believed the war would be decided by tactical superiority in individual engagements, not by operational sustainability across extended campaigns. History proved this calculation catastrophically wrong. Engineer Heinrich Steinhauser, who had worked on Jagdpanther development at MIAG, provided additional testimony to British interrogators in June 1945. Steinhauser explained that test vehicles during the development phase in 1943 showed clear evidence of engine overstress and shortened operational life. Test crews reported engine failures during acceptance trials. Metallurgical analysis revealed connecting rod fatigue problems identical to those Aberdeen engineers would document 2 years later. Engineers recommended either reducing vehicle weight, increasing engine strength, or accepting lower performance specifications. The Wehrmacht rejected all three options. Weight reduction would require thinner armor or eliminating equipment, unacceptable when facing Soviet heavy tanks. Engine strengthening would delay production for months or years, equally unacceptable. Lower performance specifications contradicted the entire purpose of developing a new heavy tank destroyer. Therefore, production proceeded despite known reliability problems. Engineers were told to do their best, improving reliability within existing constraints, but production could not be delayed. Steinhauser testified that he and other engineers knew they were sending vehicles to combat units with engines that would fail catastrophically after minimal operation. They had no choice. The alternative was not producing tank destroyers at all, while Soviet and Allied armor forces grew stronger daily. The testimony revealed the tragic dilemma facing German engineers. They possessed the technical knowledge to understand their designs were fundamentally flawed. They lacked the authority, resources, and time to fix those flaws. They were forced to produce weapons they knew would fail operationally, hoping that tactical superiority would somehow compensate for mechanical unreliability. The Jagdpanther story illustrated perfectly how this hope proved false. Aberdeen engineers incorporated lessons from Jagdpanther testing into post-war American tank destroyer development. The M56 Scorpion, developed in the late 1940s, emphasized mobility and reliability above maximum firepower. The vehicle weighed only 7 tons and mounted a modest 90mm gun, but it could operate reliably for thousands of miles between major overhauls. Similarly, the M50 Ontos tank destroyer developed in the 1950s prioritized mechanical simplicity and reliability, while accepting limitations in armor protection and sustained firepower. American designers remembered that weapons must function reliably under combat conditions to provide any strategic value. Tactical superiority in controlled test conditions meant nothing if vehicles broke down after minimal operational use. The influence extended beyond tank destroyers to main battle tank development. The M48 Patton tank, introduced in the early 1950s, incorporated reliability as a fundamental design requirement equal to firepower and protection. The Continental AV-1795 engine was thoroughly tested and proven before the tank entered production. Cooling systems were oversized rather than marginal. Components were designed with substantial stress margins rather than operating at design limits. The result was a tank that operated reliably for thousands of miles under combat conditions. Later generations continued this philosophy. The M60 series tanks, introduced in the 1960s, maintained the emphasis on mechanical reliability. When the Monet Abrams entered service in the 1980s, it incorporated a gas turbine engine that many critics considered risky and unproven. However, extensive testing demonstrated the turbine engine provided exceptional reliability despite its unconventional design. American designers would not field tanks with questionable mechanical reliability, regardless of other performance advantages. The lesson from Jagdpanther 312 had been learned permanently. Mechanical reliability was not negotiable in armored vehicle design. The strategic lessons from Jagdpanther analysis influenced American military doctrine throughout the Cold War. Field Manual 320, Armor Operations, published in 1951, included explicit sections on the relationship between mechanical reliability and operational effectiveness. The manual taught that sustained mobile operations required armored vehicles capable of traveling hundreds of miles between major maintenance. Vehicles that broke down after minimal operation could not conduct the deep penetrations and rapid maneuvers that American doctrine emphasized. The manual cited German experiences in World War II as cautionary examples of how tactical superiority could not compensate for operational unreliability. Officers studied the Jagdpanther specifically as an example of engineering excellence, undermined by inadequate attention to mechanical sustainability. Staff college courses at Fort Leavenworth incorporated Jagdpanther case studies into logistics and maintenance planning instruction. Officers learned to calculate maintenance requirements, spare parts needs, and recovery asset allocation based on expected mechanical reliability rates. The exercises used historical German data to demonstrate how poor reliability multiplied logistics burdens geometrically. A unit with 85% operational readiness required modest maintenance support. A unit with 40% operational readiness, typical of Jagdpanther battalions, required enormous maintenance assets that strained entire supply systems. The training emphasized that reliability affected every aspect of military operations. Units with unreliable equipment could not conduct surprise attacks because they needed extensive preparation time to concentrate enough operational vehicles. They could not exploit breakthroughs because their vehicles broke down during rapid advances. They could not conduct fighting withdrawals because mechanical failures left vehicles scattered across the battlefield for enemy capture. Reliable equipment provided operational flexibility that tactical superiority alone could never achieve. Jagdpanther 312 remained at Aberdeen Proving Ground as a training exhibit until 1968. For 23 years, it served as a physical reminder of the relationship between mechanical reliability and combat effectiveness. Thousands of American officers and engineers studied the vehicle, learning how sophisticated design and tactical superiority could not overcome fundamental mechanical weaknesses. The vehicle's presence at Aberdeen taught more about armored vehicle design philosophy than dozens of lectures could convey. In 1968, the Jagdpanther was transferred to the United States Army Ordnance Museum at Aberdeen for public display. It remained there until 2000, when the museum began consolidation with other Army museums. The vehicle was then moved to Fort Benning, Georgia, where it joined the growing Armor and Cavalry collection. Today, Jagdpanther 312 resides at Fort Moore, Georgia, the renamed Fort Benning, as part of the National Armor and Cavalry Museum collection. The vehicle sits in climate-controlled storage, preserved carefully for future generations to study. Museum staff occasionally display it during special exhibitions focused on World War II German armor. Educational materials accompanying the display emphasize the mechanical reliability lessons learned from testing this specific vehicle. The exhibit explains clearly that the Jagdpanther represented exceptional tactical capability undermined by catastrophic mechanical unreliability. Visitors learn that the vehicle's powerful gun and heavy armor could not compensate for an engine that failed after approximately 80 miles of combat operation. The exhibit connects this specific technical failure to broader strategic lessons about sustainable military systems. Modern military engineers study the Jagdpanther story as a cautionary tale about the dangers of pursuing maximum performance while neglecting reliability constraints. Defense acquisition courses use the Jagdpanther as a case study, illustrating how technical excellence in individual subsystems cannot overcome fundamental system-level design flaws. The vehicle achieved design excellence in armor protection, achieving near invulnerability frontally. It achieved design excellence in armament, mounting a gun that could destroy any Allied tank at extreme range. But it failed catastrophically in mechanical reliability, the characteristic that determined whether it could reach the battlefield and remain operational long enough to matter. The fundamental lesson resonates across all military technology development. Sophisticated weapons must function reliably under combat conditions, or they provide no strategic value regardless of their technical superiority. A tank destroyer that breaks down after 80 miles cannot win campaigns spanning thousands of miles. A weapon that requires constant maintenance cannot support mobile operations deep in enemy territory. Equipment that fails mechanically more often than it fights provides no military advantage despite superior performance when operational. German engineers in World War II learned this lesson through bitter experience, watching their tactically superior designs abandoned across European battlefields from mechanical failures rather than combat defeats. American engineers learned it through systematic testing of captured German vehicles and incorporated those lessons into every subsequent armored vehicle design. The principle became foundational to American military engineering. Reliability is not merely desirable, it is absolutely essential. Modern weapons systems continue reflecting these lessons. The current generation of armored vehicles emphasizes reliability as a fundamental requirement equal to firepower, protection, and mobility. The Mohn Abrams tank, despite being 45 years old in its basic design, remains in frontline service largely because of exceptional mechanical reliability. The Bradley fighting vehicle, the Stryker armored vehicle, and other American armored systems all incorporate reliability as a non-negotiable design requirement, learned partly from studying vehicles like Jagdpanther 312. The story of Jagdpanther 312 stands as a permanent reminder that military effectiveness requires sustainable engineering. The most dangerous weapon becomes useless when immobilized by mechanical failure. The most sophisticated technology provides no advantage when broken down awaiting repair. Combat capability means nothing without the reliability to reach the battlefield and remain operational throughout extended campaigns. German engineers created a tactical masterpiece in the Jagdpanther. They gave it the most powerful gun, the heaviest armor, and sophisticated mechanical systems. But they mounted it on an engine that could not sustain operation long enough to matter strategically. Allied engineers, studying the captured vehicle carefully, learned what not to do when designing their own armored vehicles. They learned that reliability must be engineered into systems from the beginning, not added as an afterthought. They learned that operational sustainability matters more than maximum performance. They learned that wars are won by reliable weapons that function throughout campaigns, not by superior weapons that break down after minimal use. These lessons, learned partly from testing Jagdpanther 312 at Aberdeen Proving Ground in 1945 and 1946, shaped American military engineering for the next 80 years and continue influencing design decisions today. The 46-ton steel Predator that once represented the pinnacle of German tank destroyer design now teaches quietly in a Georgia museum. Its massive 88mm gun sits silent. The Maybach engine, that consumed itself in mechanical self-destruction, will never run again. But the lessons it taught about the essential relationship between tactical capability and mechanical reliability continue resonating through every engineering office, every staff college, every acquisition program developing the next generation of military equipment. In the end, Jagdpanther 312's greatest contribution to military history was not the enemy vehicles it might have destroyed in combat, but the understanding it provided about why sophisticated weapons must be built on foundations of mechanical reliability. A lesson learned from systematic failure, taught through careful analysis, and remembered permanently by engineers who understood that wars are won by sustainable systems, not merely superior weapons. The captured Jagdpanther that shocked American engineers with its engine failures after only 80 miles became the teacher that shaped decades of American armored vehicle development. Its legacy lives not in the battles it fought, but in the principles it taught about engineering weapons that can go the distance operationally, not just tactically. That legacy endures in every reliable American armored vehicle fielded since 1945, a testament to lessons learned from understanding how even the most sophisticated weapon becomes worthless when it cannot sustain operations long enough to affect the outcome of campaigns. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.